on to asymptotes and holes. An asymptote of an equation or curve is a line where the distance between the curve and the line approaches zero but never get to zero as the x or y continue to infinity. So what this is explained as, I'll show you an example on here, is that for my equation there's going to be a vertical asymptote that runs along where my finger is. And the vertical asymptote, the equation will come ever so close to touching this line, but it will never touch it. And it just means when the equation is at extreme values, it'll approach this line but never touch this. The asymptotes occur because the x or y value can never equal that number. So in the denominator, there's a root of 2, as we see right here. This means that when x equals 2, y equals 0. Because when we plug this in, we know that when you have a root, your y value equals 0. So when we plug in 2, y equals 0. Because 0 would happen to be on the bottom, the function would be 2x minus 3 over 0, or whatever this number happens to be, 4 minus 3, 1 over 0, making it undefined, and the equation come close to 2, but never meet it. Because you have 2 over a number, or over 0, you will get close to touching that number, but you will never equal that value. There's no number you can plug in that will make the equation equal 2, or x equals 2. And therefore, that's why the asymptote occurs. And a little note here is only concerned with extreme values of x, because in some occasions you will see that the equation or your function will cross over your asymptotes near the origin, and which actually happens in my case where the function crosses over. But when you look at extreme values of x or y, the function will approach that asymptote but never cross over it. A hole is a point in the function where x cannot be that value. On a graph, there's literally a hole and is represented by this little point here, a circle to represent a hole. A hole occurs when an x value sets both the denominator and the numerator equal to 0. So what we have here is a cubic in factor form and a quadratic in factor form. What we see here is we have an x minus 1 in both the numerator and the denominator. They cancel each other out because you're dividing x minus 1 divided by x minus 1. It doesn't mean that this is now not a quadratic over a linear. It just means that there is going to be no point or a hole at x is equal to 1 because they cancel each other out. That value is now non-existent and will make the numerator and the denominator equal to 0. So what you will have is, like I've written here, is when x equals 1, the equation becomes 0 over 0. This has no value and places a hole in the graph. So that's why there's a hole at that point. Now more specifically to my function, there's no horizontal asymptote, and this is because horizontal asymptotes only occur when the degree of the numerator is equal to or less than the denominator. And there's no vertical asymptote. This is because there is a vertical asymptote, and this is because there's a root or an x value that will make the denominator equal 0, meaning undefined, and x will never equal that value. So as I previously explained, you'll have something over 0, a value over 0, and it means that the graph will never get to that point which made the denominator equal 0, because there's nothing that you can plug into the equation to make x equal 0. There is an oblique asymptote, and we can tell by looking at the equation because the degree of the numerator, or the leading coefficient of the numerator, is exactly 1 degree larger than that of the denominator. So like we see here, x cubed as the leading coefficient is clearly 1 degree larger than 2x squared. So the horizontal asymptote. The denominator keeps numerator at an equal distance from 0 or roughly close distance from 0. So what we see in the sketch here is when you have an horizontal asymptote, the equation will come close to this line, and it'll stay, and see how the horizontal asymptote is parallel to that of the x-axis. And this is because you're dividing the numerator by the denominator, and if the denominator is a bigger number, it'll pull that equation closer to 0, or the same distance to 0. An oblique, the numerator pulls the denominator away from 0 because of larger number on top and dividing by a smaller number. So we have a larger number on top, which is pulling away from 0, and then what we have is the denominator, which is a smaller number, trying to pull it slightly back, but not enough to get it. So what we're left with is this diagonal here, and that is what your oblique asymptote looks like, because your numerator is pulling the equation away, but the denominator cannot pull it back. So looking at my equation in factored form, we can see there are no holes because there's nothing to cancel out on the top and the bottom. So therefore there are no holes. Vertical asymptotes, and as previously found, there are roots of the denominator, and these are at 3.1085 and negative 1.6075. And x can never equal these numbers on my equation. And horizontal asymptotes, as previously explained again, there are none. There will be an oblique asymptote, but not a horizontal. You cannot have both an oblique and a horizontal asymptote. So now, trying to find the equation of our oblique asymptote. So what we're going to do is use long division to find the equation of the line or linear equation at which the rate of the numerator increases distance from 0 at infinite x values. Or, in other words, how much pull from the numerator compared to the denominator. So what that equation is of how much the numerator is pulling away from 0 compared to the denominator. So here we use long division, and what we end up with is an equation of half x plus 1.75, which would be our equation of the oblique asymptote. What we're left is a remainder of 8.25x plus 25.5, and another way to write this would be 8.25x plus 25.5 over 2x squared minus 3x minus 10. Because as we see here, this is the denominator of my equation, and we are left with this remainder to plug in on the top. And just another way to express the remainder. And we'll take a look at this on here. I have the asymptotes plugged in here, and we see that the oblique asymptote, this blue line here running across, and as I said before, we're not worried with values close to 0 for the asymptotes, because as we clearly see here, the function dips below the oblique asymptote. But as we go farther down, further down the line, we see that they begin to start to come to meet each other, and that is normal behavior. However, around the origin, the function can do weird things, and this is why we disregard anything around the origin. And again, as we see here, for the vertical asymptotes, the equation will come close to touching this line, but will never equal it on both sides. We see anywhere we go down this, up or down this equation, the function will never equal those asymptotes.